Okay. So last time we were talking about embedded um, block statements. So kind of the direction we've been going here is down a path of more and more complex parse structures until we got to this thing where this almost seems borderline ridiculous, right? Uh, where we're having to make special cases for every single one of our parses. So if we roll back in time and we think back to early programming language designers, this may have been kind of the first way they attempted to organize a programming language. Similarly, if we think about it from the perspective of databases, early databases were done as flat files, and then they had to kind of create data structures to better organize stuff inside. I mean, so if we fast forward to um, relational databases, we see them deciding that, they're going to store data in the form of tables with linking between tables with, foreign keys, primary keys, things like that. And then even within tables, we've given fixed constructs for ways that we can represent data. So we're going to have to look at something similar to that. The hope is that for this homework assignment, it was doable but very tedious, because you had to follow this algorithm to really go through individual words, and whatever you did for this last assignment doesn't necessarily apply to future stuff. You might have to create different one-off type things. So the idea here, let me hide this. How do we consistently parse code? If we look at modern programming languages, first of all, if we look at our programming language here, if we look at our programming language here, we see that we're having to represent all of our stuff on one big long line right now, which makes it hard to program in this. Certainly, this makes it difficult for a human being to read, right? Our preference would be for this to look something like maybe this. Something like that. This code is certainly easier for a human being to read. But right now, our code doesn't allow for that, because the way we're parsing our code is by just reading in from this file and splitting on semicolons and just kind of going to town with that. So we could come up with a new style of processing code, because we would certainly say, as programs get more and more complicated, a human being is certainly going to prefer to write code like this, not being stuck to a single line, right? This should look a lot more familiar to you. Similarly, as our language gets more and more complex, we don't want to have to create these one-off, fairly complex algorithms that probably still have problems with them. They probably still require something very, very, very specific. And that's where something called a parse tree comes into play. So a parse tree is a data structure that represents I'm going to call it the tokens of a formal language in the desired, I'm going to say order. Let's call that a reasonable approach. I'll show you an example of this. Actually, this one is probably a reasonable enough. Well, let's see if I give us a code example here. They're doing it as sentence structures. That's fine. Okay, so you might have something like, it would probably look more like this. Let's see, just give it to me as a decent picture. Okay. So we have, for us, it would be a program. For this, we're dealing with the English language. This is a sentence. Okay, so the language is made up of sentences. So we have a sentence. So we have a noun and a verb part. So the sentence is expecting a noun part and a verb part. That's what it's expecting. Now, as we keep going through it, as we're parsing our code, we'll talk about how the parsing actually occurs shortly. But as we're parsing our code, this is kind of like, you could think of this like a, one of our while loop or something like that, where we're expecting, something followed by the word do. So these are going to be the expected pieces of all sentences. So as we're going through, we find the noun part and we attach that to the noun part portion of this, and how we actually represent our tree will kind of be up to us. Then we're looking for the verb part. We found the verb, hit in this case. The sentence is, so can I get rid of this? Oh, that just shows up below, got it. So John hit the ball is the sentence that we're parsing here. Okay, so we get to the verb part. Here's the verb, hit. Here's the noun part, which is determinate, and the noun, the ball. Okay, so if we imagine this as syntax for our programming language, where it says that, all while loops look a certain way, just like this says all sentences look a certain way, we can go through and we can build out this tree with our expectations. Now, what this supports, notice that we have an NP here and we have an NP here. So it does allow for things within things. So it gives us that representation. And visually, as a human being just looking at this, we can see that this noun part must have been contained at a lower level in the structure than this noun part, because it's lower down on the tree. All right, so if we can somehow turn our code into a data structure that looks like this as an intermediate step before we interpret. So really we're looking at parsing happening in this form. So we're saying parse syntax into a parse tree. Turn, well, we could probably still say parse tree. Parse tree into objects. Run interpreter on collection of objects. Okay, so we're splitting our parse step up. Instead of taking syntax directly into objects, we're taking syntax and turning it into a parse tree first. And then from that parse tree, we're going to then get our actual objects. So we're turning what used to be one step into two steps. Now let's use an example here. Okay, so here is our while test. Now, well, let's not worry about how we're getting it into this tree for right now. Let's just represent it as a tree right now. All right, so what we'll do is we have a top level thing, program. Okay, so here's our program. And our program is going to be a collection of statements, right? So we're going to have statement, all things hanging off our program that we operate off of from left to right, we can say. But in this example, we have a single statement. So I'll just put it directly underneath this guy. Actually, let's do this. We'll put the little line in there just so it visually will end up looking like a tree. All right, so there's our first statement. Now this kind of statement we've bumped into is a while statement. So here's our while statement. Now let me ask you this. Does the word while or the word test, these aren't important parts. As soon as I see that I have a while statement here, what am I going to do? I immediately expect, why can't I click? A test. And a statement. I immediately expected those two pieces because that's what the syntax for a while loop says. Okay? A while loop has a test and a corresponding statement. That's what while loops have. So now, what's a test? A test has an expression and another expression and an operator. Expression, expression, op. So as soon as we see something that's of type test, here, I'm going to stretch this out some here. So we run into our test. And then the statement associated with this guy. So, well, let's do our test. So this is E. So this is going to be some type of expression. In this case, it's a resolve expression. Let me do this in, well, let's show the tree. This is fine. So this is going to be a resolve expression, and this resolve expression ultimately just has a variable name associated with it. In this case, it's E. We'll try to do it as a lowercase e. Okay, there we go. Then we have our op. Our op in this case is greater than. And then we have our other expression, which in this case is a lit expression. That guy is a 0. All right, so this is our initial test, followed by a statement. So this statement, now we're ignoring the word do. That's not part of, that's part of the human syntax, but not the full syntax. Well, not part of the important syntax, let's say. So now in this case, the type of statement we have is a begin statement. Now notice a while does not require a begin statement. A while requires a statement. And a particular statement we ran into was a begin statement.
I think it should say block statement.
Oh, well, yeah, it's fine. To match what we had. Same thing, but you're right. All right, so we have our block statement. And this block statement is going to be a collection of statements that go into our block statement. Okay, so just like a program is a collection of statements, a block statement is going to be a collection of statements. So in this case, just so I can organize it a little bit, we have 1, 2, 3 things. Actually, I could probably read it better in here. So we have 1, 2, 3 things, 3 statements that are part of this block statement. I'm going to go ahead and steal this. So we'll have a statement. We'll have a statement. We'll have a statement. And I'm going to go ahead and draw the lines in here because now things are going to start getting spread funny. Good news for us is as programmers, we don't have to worry about visually representing this when we actually go to code it. We're just doing this for human eyes right now. So we happen to know that in our particular example here, that our block statement has 3 statements coming off of it. So this is where we are here. So the first statement is a print statement, which takes in an expression. Actually, we're just calling them up above, just single words. Okay. Now, one thing I want to point out here as we're going on, we want to keep doing this, is we're effectively visualizing the first and second part of the parse here. We're not just dealing with a generic statement, we're dealing with a specific kind of statement. We haven't made the objects yet because we haven't gone through the parse tree, but we're representing the details of what we are parsing as we bump into those words. Those words have meaning. When I bump into a while, that starts off the process of saying, we have a statement, and that statement is, in this case, a while statement. How do we know? Because I ran into the word while. That's how we know. It's one of the reserved words in our language. So here in a few minutes, we're going to talk about the idea of reserved words, separators. You can call them delimiters, separators, whatever you want. And these are things that we're going to use to determine whether or not something we're looking at as we're going through our string here is of a certain kind. So we can decide how to add it to our puzzle. All right, so we'll do that as our second pass. Let's get our tree represented here. Okay, so we ran into a print statement. This print statement takes in an expression. In this case, the expression is a resolve expression. E. That was our first statement here. Then we have another statement. Now we knew we were done with that statement because we hit one of these separators. Okay, we'll talk about how do we actually tokenize based on that kind of stuff, but we hit a separator. All right. So this guy says, don't do anything with this symbol, but also we've completed the current statement. So we're not going to put this anywhere, but we are going to, as we're building our tree, bounce up a level and add another statement to this block statement. Okay. So next thing I'm reading in is an update statement. So we have another statement. This particular kind of statement is going to be an update. What does update expect? Update expects a expression. Actually expects a variable name and an expression. That's what update expects. Those two pieces. In this case, our var name is A. Kind of a waste of time probably, but that's fine. Okay, now notice that this is not a expression. This is just a variable name. It's just a symbol. Update then expects an expression. What kind of expression do we have here? We have a literal expression. And in this case, it's a 10. Then we hit a separator or a delimiter or a terminator, however you want to view this. We know we're at the end of that statement. So now we're on to our next statement. So we bounced back up. We're adding another statement to our block. Stretch this guy over just a little bit. We're going to start getting pretty tight here in a second, but that's okay. So this is a statement. Specifically, it's a while statement. And a while statement expects a test and a statement. So as soon as we bump into while, we know we're going to have two different kinds of animals here. We know we're going to have a test and a statement. So here's my test, a greater than 0. Give myself some space here. Maybe we'll be able to squeeze it in. So a greater than 0. So for my test, the left-hand side is an expression. So to test, I'm testing against an expression. In this case, my expression is a, so that's a resolve expression. I'm going to go ahead and draw the line so I don't get lost here. There's my resolve expression for my test expression. A test expression is going to be an expression, an op, and an expression. So we know we're going to need these two things as well to be part of our test expression. And what I'm going to do here is I'm going to drop them down and over. There's our resolve expression. Here's our op. And here's the right-hand side, which is an expression. So our resolve expression is, what was it, A? Op was greater than. Op is greater than. And then the other side of the expression is a literal expression, in this case 0. So that's our test expression side of that. And then we expect a statement to be part of the while. Here's our statement. And the statement is going to have in it a begin statement or a block statement. That's the kind of statement we bump into. Have we been representing it as block like that? Well, that's how I said it before, so that's fine. So it's a block statement, which is going to be a collection of statements. I happen to know I'm going to have two statements here. Actually, do I have two? Begin 1, 2. Yeah, I have two. So actually, I have the syntax written a little funky. This should be back here. This is one more statement at this level here for this while. So I have a test, I have a statement, so we actually have a fourth statement. This one's going to be pretty hard to represent on my picture here. All right, so we'll get to that guy here in a few minutes, but that last statement there is actually the statement here that's part of the first block statement. 1, 2, 3, 4 things part of the first block statement. 1, 2, 3, 4. Now we're in our inner block statement. This guy right here, we have two things, a print and an update. So this block statement has two statements associated with it. And this is going to start looking, that's already a little janky. So I'm going to drag these guys way over. Just to squeeze it all in. So now I can have, well, I'm going to have two statements. That's probably okay. That's probably, well, we'll adjust it as we need to adjust it. Get my next shape in here. So this block statement has two statements associated with it. We have a print and we have an update. I'm going to go ahead and put both of those in right now, just for my own sanity as I'm representing this. We're not talking about how did we build this yet from code, just ultimately that it's built. Statement, we have a print statement, we have an update statement, print and update. A print statement is going to, in this case, be a resolve expression. What am I resolving? I'm resolving A. I already have that somewhere. Resolve expression A. Okay. And then for my other one, it's an update statement. Of course, it's going to be several things. Okay. So it's going to be an update statement. I got one of those somewhere, don't I? Nope, it's my first one. Oh, I already wrote the update part. So update statement, and this guy, for an update statement, we take in a variable name, and I do have one someplace else. This guy is expecting a var name. I have one up here. And I'm expecting an expression. So whenever we run into an update, we know we would need a variable name and we need the associating expression. Variable name here is A. The expression is a do math expression. And our do math expression is going to have an expression an operator, and an expression. So let me shorten this branch. Let's go there with it. All right, so in this case, we have an expression, an op, and an expression. Op and an expression. We're actually still dealing with this one, right? We're in our block statement. Here's our print. Here's our update. So we're on this one. So we have a resolve expression and a literal expression and a minus sign. Go ahead and put my minus sign in here. Then we have a resolve expression, and I'm resolving on A, right? Steal this. All right, so I have a resolve expression. And the right-hand side is a literal expression. One. Steal this literal expression and we'll change it. Jeez. So it's a 1. Shrink my font down, I can fit some more stuff. And our 1. Okay. So then we hit the end of this block statement. And now we have one final update. And this update is going to be pretty similar to the update we just did. So I'm going to steal all this stuff. I'm going to need to squeeze that in over here. Let me see if I can do something here. It doesn't shorten the lines. It's a little janky. That's probably too janky. I know some of these things aren't really readable right now, but I think we have enough stuff that is readable that it's, you'll know what it's supposed to say. Okay, so now we should be able to move this all over and down. All right, so there's that statement. I think we could squeeze it in over here. So our last thing is an update statement like this guy. This update statement will have of our name, and an expression. My var name is E. My expression is a do math. Expression is a do math, and it is E minus 1. Okay. I think that fits in our our program in this case. So this parse tree is the data structure version of this string, me parsing this string. Now, we did this as humans, where we went through and we just we picked out the pieces that we needed. We put them in this organization. So now what we need to do is we need to capture this process that we just did right here that says, I need to turn this string into this structure. And we need to decide, how do we do that? So there's really two next steps, right? Two next steps. One of those steps is to build a data structure to represent our parse tree. And then the step after that is walk through our string and add elements to the parse tree data structure. All right, that makes some sense. All right, so before we go any farther, does anybody have any questions about what we did here? I know you can't read necessarily all of it, but up this top stuff should be a little bit easier. Do you understand how this ultimately is a parse tree representation of this? This is our before, and this is our desired after. This is the result we're desiring right now. So any questions about that?
I think definitely all these things make sense, but my question is, should we have to do it this way, or it's like we almost need to redo part of our parser?
We're basically definitely redo, because we're basically saying, if I am an old programming language writer, so we started off today saying, let's roll back in history. Because one of the things that I like doing is I like to put ourselves in the shoes of, the pioneers of the industry. So if programming languages had never existed before, that's what we did. We invented a language, right? Programming language had never existed before. And we said, okay, well, this is what our language looks like. We're going to go ahead and put stuff. This is just file IO, right? We're going to do stuff in a file. Now I'm going to have each line of my file mean something in my programming language. This is the idea that maybe the very first program language writer would have been thinking, because he's not necessarily thinking at this point about all the little caveats, all the things he might run into. He's also probably not thinking about the scale that future programming languages will get into. When we had our early computers, they weren't complex enough, or really programmable computers. They weren't powerful enough to really imagine large scale applications running on them. And because of that, human beings were not really imagining the multitude of different applications that we can represent today with computers. Okay, so the target of what the first programming language needed to be was probably different than the target of what a modern programming language needs to be. If I move it outside of programming languages, let's look back to the early cars. So, when everybody was riding around on horseback, and then they decided, oh well, we need something else, or what's the next step in transportation, and let's say they came up with the car. It was probably there was bicycles before that and stuff like that, but just let's make the leap to the car. Okay, so the first car, what did it need to do? Well, it needed to replace the horse. Well, what does replacing the horse mean? Well, it needs to allow probably one or two riders. They probably, in the ideal world, would have said, well, it needs to go at least as fast as the horse goes, but at the same time, it also needed to not get tired. As long as you kept fueling it, regardless of how much you fed your horse, it would eventually get tired. So there were some initial constraints. If you were somebody who was currently riding horseback, and then you were having to decide, well, what's going to be better? What's the next step? You would have had to make some decisions there that maybe were only supported by what you already knew. So maybe the first vehicle, you weren't necessarily worried about absolute top speed. You weren't necessarily worried about, you weren't thinking about the wheels and how smooth the ride is, because you're kind of thinking, oh, horseback, it's what we're doing now. It doesn't have to be any smoother. So there was all sorts of considerations you didn't take into account when you came up with that first car. But then once we had that first car, then we started thinking about, oh, how can we make this better? And then once we had that, how can we make that better? How can we make that better? And we ran into those things each time as we hit the limitations of the current tool that we were working with, right? God made the horses, so we couldn't really upgrade that. We can do things with saddles and things like that to make it more comfortable, and and that kind of stuff. And but then once we invented the vehicle, we had some more latitude to make upgrades, more changes, things like that. All right. So to Blade's point, because this was our first, because this was our first programming language, if we put ourselves in the shoes of one of those early inventors, we didn't necessarily see how complex this thing's going to get. We just let it grow. We said, oh, well, what do I need to be able to do first? I need to be able to remember some stuff. I'm using my computer's memory. Great. Okay. Now I should be able to ask some questions. Cool. Now I need to link some of those things together. Well, why am I doing any of this? Well, I probably want to be able to do some math. Now I want to be able to do some stuff multiple times. And instead of doing a single thing multiple times, I probably want to do multiple things multiple times. So as our needs grew, as we kept adding features to the language, we started seeing that, oh, the approach we've been taking. So one of the things we've been focusing on the last several weeks is this idea that if that's whenever we add a feature, it was that same pattern, right? Add it to our document, add it to the parser, add it to the interpreter. Over and over and over again. Every single time we added a feature, we did that same pattern. Now, what we've noticed in the last couple, starting a little bit with do math, but palatable with do math, and then more so here with our block statement, where we can have block statements inside of block statements inside of block statements, we started recognizing that I'm effectively doing these one-off parsers for this thing. Now, is that the end of the world if you know, the light at the end of the tunnel? If the light at the end of the tunnel indicates that, oh, I only have one or two more features to add and then I'm good. Maybe you decide, okay, it makes sense. And I'll just go ahead and write these, you know, one-off special kinds of parsers for this and move on with life. But I think we already can see that even if you have the stuff for the homework assignment working, it does require that you write the code in a very specific way because you probably can pretty easily break it. By adding a space, you know, we already saw that like last time where, you know, there was extra spaces here and there, stuff like that, where, you know, we were having to just put trims all over the place. You know, we were basically doing a lot of patchwork, you know, saying, oh, okay, well, in order to fix this, I just need to trim here, and trim here. It's not really the right fix, but it's a fix. And by the time you're done, you have this giant application that just has all this patchwork left in it. And we already have an example of an application that exists today. That's the result of that actually causes a pretty big problem in our industry, and that's with web browsers. So because the early web browsers didn't make web developers write, you know, correctly formatted HTML, like kind of rolled with some of the punches. It didn't make you close every opening tag, stuff like that. Now what you have is you have code bases for these web browsers that are backwards compatible with old school web pages. And now what you've created is the situation where you have to test the new website on all the different browsers, or at least all the different popular browsers, to make sure they look good on the browsers that your clients are likely to be using. Because the base code base for those things had some flexibilities that allowed for non-proper HTML to be written. And if you've ever played with it before, most of our modern web browsers have a setting for XHTML mode, which says web pages have to follow proper HTML format. Every opening tag has to have a closing tag, so on and so forth. And if you do that, you'll notice that a lot of websites break. Well, why do, I mean, even modern websites, they break or they don't look right, whatever it is. Well, put yourself in the shoes of a web developer. If you're a web developer working at Amazon, you know, which is a modern website that people are constantly making updates to, things like that. When you make a change, how are you testing it? You're testing it in the popular browsers, right? You're making sure that it works in the popular browsers. Well, the standard that the popular browsers are holding you to is not perfect HTML standards. The standard they're holding you to is, you know, HTML-ish standards. Now, nowadays, companies are starting to work towards making standardized HTML and improving some of those old things. But you imagine over the years, you know, which is kind of the example we're trying to portray today, over the years, there was just a lot of patchwork that went into kind of getting this thing put together in a way that that just kind of works, which then allows the people creating content for it to be lazy, or, you know, they don't have to follow all the rules because they're developing content for a tool, and that tool allowed them to get away with some stuff. So the tool wasn't making them stay disciplined. So punchline is that if we put ourselves in the shoes of a language developer from years and years and years ago, What we've just done is we've kind of written our thing until we got to the point where it's saying, you know what, if I want my language to keep growing, I might need to take 2 steps back in order to take 3 steps forward. So that's kind of to what you were asking, Blade, is do we need to represent it like this, or do we actually need to go back and update our parser? We really need to update our parser to follow a new guidance where we take our text and parse it into a parse tree first, then turn it into objects. Where we are taking from text, we're going right now from text directly to objects instead of this intermediate form. And this isn't just for block statements. This is for all statements. Okay, we're basically upgrading the way that we parse so that future features can be added with less special cases, less patchwork, things like that. Does that make some sense?
My question is actually this. Everything makes sense, but I'm just curious, was this in your original plan?
Oh yeah. This is part of language design.
Just curiosity, why not you were doing this initially?
Because if we do this initially, then we wouldn't see what beginning programmers would have run into with normal parsing. This is a weakness of parsing, but not necessarily a weakness that they would have seen from the get-go. This is just like when you first learn how to program, one of the things I like to do is I like to have people compile from the command line, when they're writing a Java program, as opposed to starting directly here in Eclipse and just hitting the play button. So you start off with the older way of doing it, and then you see the limitations, okay? Because we're not necessarily just looking at, here's the current best practices, because let's take the best practices of anything. I don't know, we'll try to take some, let's take driving. Driving is a good example, especially since last year in the research class, a lot of folks did stuff with like autonomous driving. All right, so, you have 10 human beings. Do they all drive identically? They all drive similarly, right? But some human beings might decide that a certain speed is safer than another speed, or they slow down for turns a little bit earlier, a little bit later than other people. But there's kind of this like common guidance to driving that people have. So we can just call that good driving. So a modern day person could look at somebody else's driving and decide, are they a good driver or not? Okay. Now, do you believe that good driving today is as good as it will ever get? Or do you think that as things continually change, as traffic patterns change, or the speed of vehicles change, or, with autonomous vehicles, we're already having this to some point, but, you're having this kind of hybrid collection of different kinds of vehicles on the road. Some of our vehicles are being fully driven by a human being. Other vehicles are being driven by a computer, and then something in between, right? Even cruise control makes a difference, right? So some people when they're driving, they're controlling the speed of the car at all times. So their speed's going to be a little bit more variant, depending on how hard they're hitting the gas pedal. Whereas somebody who has cruise control, they're going to go 70 miles an hour consistently on the interstate. Now, that person who's going 70 miles an hour consistently on the interstate, they're also going to have to now keep track of what's going on around them traffic-wise, because if the people in front of them slow down to something less than 70, well, they have to slow down to something less than 70. Well, then we came up with an upgrade to that, right? We came up with adaptive cruise control. Do any of you have adaptive cruise control in your cars? Where you have the cruise control set at like 70 and the car in front of you slows down to 50, your car will automatically slow down to keep a certain distance behind that car without you doing anything?
No.
Yep. So that I've had it in my last 2 cars. So so I get on the interstate, I set the cruise control at whatever the speed limit is, and then I just chill in my lane and listen to my audiobook. and my car will automatically slow down for the, you know, cars in front of me slow down. And I just have a setting that says how far behind them do you want to stay, 1, 2, or 3 car lengths. So it's changed what we say is best practices for driving. Now, you know, what's interesting in a hybrid system like we have today is, let's say that I do a lot of driving and I become very accustomed to my adaptive cruise control. And then I go on a trip somewhere and I rent a car that doesn't have that adaptive cruise control. I'm probably a little bit out of practice for the, you know, the old school. What if I just had cruise control? Or what if I was, you know, it was a place that the rental cars didn't even have cruise control. I just had to hit the gas pedal. You know, even automatic versus, you know, manual transmission. You know, stick shift versus automatic transmission. Well, you know, when you're younger, stick shift seems cooler. It's more fun to drive that way, you know. But then you kind of think, well, I just want it to work. I just wanted to do it for me. But let's say that you're somebody, and this would be a common thing, is especially since there's other countries that where stick shift is basically the most common type of vehicle. So let's say you're an average American driver who probably uses, at the very least, automatic transmission. They don't know how to drive stick shift. And then all of a sudden they're on a trip and they rent a car in, you know, in wherever, Thailand or something like that. And let's say that the car is a stick shift. They might not be able to drive that vehicle because they're not competent with that vehicle. But once upon a time, best practices for vehicles was that, oh, stick shift was actually an upgrade to a single gear transmission. Like, oh, you want to go different speeds, you want to have different gears so you have better fuel efficiency, things like that. Oh, we're going to give a human being a way to manually change those things. So over the years, we have adapted what we thought was best practices. Something that would have been very much the common way of doing everything years and years and years and years ago would have turned into something that we would have, that we don't even view as being even a reasonable idea today. So that's kind of to your point, Blade. Like, well, why don't we just start off by doing it the best way? Well, even what we have as our best way today might not be the best way 20 years from now, something like that. So from a language design perspective, it's better for us to appreciate how we got to where we are today by hitting those fences on our own, going through those, going through those same kind of hoops that early language designers had to go through. Because I'll tell you, even doing what we're doing today, this approach isn't even identical to the way it's actually done today. Today, there's even a third step where we gather collections of symbols and things like that first, then we turn it into a parse tree, then we turn it into a collection of objects, then we actually put it through the interpreter. And then it gets even more complex when we get to the point where we say, oh, well, we're going to do this as a compiler and ultimately translate it directly to the CPU, something the CPU can eat off of, and not rely on there being an existing operating system that could run an interpreter. Okay, so we're kind of seeing the different layers here, but really the goal of what we were doing before is this is good enough for a while. And we can even say it's probably good enough for making a full-blown programming language that does most of the things that modern day programming languages do. We can get by with this. But at what point do we say, you know what, every single time I add a feature, it's like pulling teeth. And things would be so much better if I did something a little bit different that might take me some time to update the whole system, you know, kind of like when you do a whole operating system upgrade. And, you know, now there's a new way of doing things that might make you have to go and modify some of your old applications because they don't quite work right anymore. But once you go and do those modifications, future updates to your program become much easier, would be the ideal. Something like that. But even just from the perspective of, hey, I want to write my code to look like this. instead of having to put that big long line all on a single line, that's going to be much more difficult for a human being to write or read. So even from the ability to write our code, forget about reading it, we're starting to hit limitations where our statements are getting so complex that anything, I mean, really, this isn't that impressive. We would, as a modern day programmer, we would look at something like this and say, oh, that's pretty simple code, right? There's nothing major going on with that. But when we looked at it from our, hey, I had to write this perspective, I'm not sure we would want to write something much more complex than this. Does that make some sense?
Yes, I understand. You like to let us go through from the beginning to like a more advanced approach, and I think it's really appreciate your thing. We should all appreciate the historical approach rather than jumping to like what is the most advanced thing right now.
Right. But the thing is, it's not just what I do from a teaching perspective. It's also what I do for myself. When I learn about something, I want to learn the basics. And a lot of times the basics are going to be fairly compatible with the old way of doing things. So even with you and I, when we started messing with the 3D printer stuff, you know, we ran into problems that other people had already solved. But we had to run into those problems ourselves in order to appreciate how some of those fixes took advantage, fix those things. And then we were able to then, I'm sure with all the stuff you've done over the last year with the 3D printers, for example, you've come up with your own ways of doing some things that maybe are better than some of the solutions online, or you find them more convenient or whatever. But in order for you to have the background, in order to invent those methods, let's say, you had to have some of the you had to bump into the real problems that would have existed before, instead of bypassing all of that and just having it work. Because you're somebody who needs the theoretical background because you're solving future problems, as opposed to somebody, do you need to be an expert in how cars work to drive a car? No. But if you're inventing things for cars or cars themselves, you certainly need to be an expert in how cars work. And being an expert in how cars work is also being an expert in how cars used to work and why was a certain thing an upgrade, because that's going to give you some lessons for what the next upgrade is going to be. So this is the difference between people who need to be experts in a field versus people who just need to be competent at using a tool. I think it's an important aspect of how learning should occur, even though it takes longer. And it does take longer, right? To fully understand everything that's under the hood and go back and do things that aren't necessarily the way things are done today does take longer, but it creates a solid foundation for which you to potentially innovate moving forward. All right, so we're only adding one more layer here. It's modernly, it's even more complex than this. All right, so next two steps is build our data structure to represent our parse tree. So this is completely separate from a programming language. I'm not even talking about parsing syntax yet. I'm not talking about what a programming language looks like yet. I'm talking about we need to create a data structure. We need to create some software that allows us to represent things that look like this. Forget about what those things are, right? Because we start off, we're saying, well, I need to create something that's going to hold an animal that I'm calling a program. Well, what's a program? A program is a collection of statements. So that means off of this top node, so we can call this like this guy is a tree. I call it a parse tree. So this guy's a tree data structure. What does it mean for something to be a tree data structure? Well, as you learn about this stuff, you may have run into special kinds of trees, right? Like when I say, what is a binary tree? What does that mean to you? As computer scientists, when I say binary tree, What does that indicate?
Making a tree which represents the nodes.
Okay, so part of what it says to you is that order is implied, right? That things happen in a certain order, but that order is achieved through a couple of things. One thing is that no node has more than 2 children. And another thing is that everything to the left of a node is less than or equal to it. And everything to the right of a node is greater than it. You've applied a rule, a constraint to that tree. So a binary tree still looks like a tree, but it's a much more refined tree because it has to follow a very set of rules, right? Okay. Now, where did we get the name tree? Why do we call these kind of data structures trees? What do you think the original person who came up with this was thinking?
I think he called like a hierarchical structure rather than a tree.
Well, but why do we call them trees today? Is tree a made-up word? What does tree mean to you? You walk outside, you're going to see a bunch of trees, right?
It has a single root and have some branches.
Yep, single root and branches. This guy's kind of like an upside down tree. Actually, this guy right here is kind of like one of those bonsai trees from the Karate Kid movies. Kind of is what he'd end up looking like. Okay, but you know, when we walk outside and let's say you walked outside at campus. Concordia has a lot of trees surrounding campus. Even though, you know, as human beings get more and more, you know, we start building more and more buildings, we keep knocking down trees, but there's still plenty of trees right around campus at Concordia. So we're going to walk and we're going to look at 5 different trees. Are all those trees going to look identical? No. Or does each tree kind of have its own uniqueness? More or less branches, taller or shorter, things like that, right? Trees kind of come in all sorts of shapes and sizes, but they all start with a single root, right? A single trunk that then branches out into all sorts of different sub-branches and things like that, right? That's what a tree is. So when we go outside and we decide, oh, well, I need to create a data structure, or we actually maybe work the other way, it says, could I use that shape, that idea of a tree, and could I use it to represent things, and how? Well, binary trees, they come in the form of us saying, oh, I'm going to apply some rules to what all my trees must look like. And now I can say, okay, well, these guys are now used to represent data in order. All right. Is this guy right here data in order? Does this follow like binary tree rules? Not at all, right? My only ordering thing here is I'm going to say I'm going to go from left to right and then top to down, right? So, you know, I'm organizing my tree as like a program is a collection of statements. In this case, I have a single statement. If I go back over here to Eclipse and I say, well, this is my entire program, I'll have program at the top. This will be one statement in it, 2, 3, 4, 5, 6, and 7. So I would actually have from this main root 7 statements coming off this guy to represent this computer program. That's pretty simple. Okay, so this guy starts, you mentioned a few minutes ago, the hierarchical type of thing. It looks like a tree, so we're going to call it a tree. It doesn't really matter what you call it, but us calling it a tree implies that we're going to have branches off of branches off of branches, and that's, you know, that implies a certain kind of way we might implement that. All right, so we have some specialty kinds of tree data structures. So we might say that all trees have a single root and then the ability to have branches come off any individual branch, which could allow us then to get some pretty complex looking trees. okay? But let's call it generic trees. Generic, or a lot of times we call them n-ary trees, do not have a defined shape. It's just a hierarchical way of describing data. Okay, so that's what a generic tree data structure is. And really what we're representing here is pretty much a generic data structure. This thing's just all wild based on what code I ran into, right? A program is a collection of statements, where a statement is one of several kinds of statements. Right now, our language supports several different kinds of statements, but certain statements exist in a form that allows them, that says what they must be. So if I bump into something that is a while statement, I know that all while statements have a test and a statement, a body. Okay, so if this is the question, this is the body. That's what makes up this guy. Just like in the example from a little while ago when we were looking at this, which is, looking at an English sentence structure. So this is our program. This is a sentence. All sentences follow this structure. And this is how this particular sentence can be mapped, diagrammed into this structure. All right, so no, actually, I'll leave it like that for now. It's not going to hurt anything. How do we implement a parse tree? Now, there are tools out there that allow you to describe your language, and then it will generate the tree structure for you. And then from there, so there are tools that exist that allow program designers to not have to focus on writing the implementation of a parse tree. The parse tree implementation already exists as its own software application. So you actually just have to describe the symbols of your language, the separators of your language, things like that, things that we're going to be stumbling into here. You just have to describe those things, and then it will turn it into a parse tree for you, because they've written a generic parse tree that operates off of various kinds of statements in your language. So you have to describe those using, automata nomenclature. So a way of writing formal languages that can be, unambiguous, and then it will generate the tree for you. Well, we're kind of putting ourselves in the shoes right now of, oh, well, what if I was the person who was writing that generic tree data structure, but rather than letting people describe any kind of statement to me for that, I'm just going to hard code my statements in initially. And then to your point, Blade, then what happens next? Well, once I've added, 5, 10, 15 different kinds of statements, I might say, you know what? If I wrote this more generically, I could describe my statements in even another way and allow my tree to adapt to any kind of statement as long as they were described using some sort of formal language. So now we would then go back and reinvent again, building another layer that lives between our parse tree and our syntax. So rather than building a brand new, rather than just continually tacking on the types of statements that our programming language supported, we would have a parse tree that understood how to read in any sort of statement formal language, and it would generate the branch that was associated with that. Okay, so question is how do we actually implement a parse tree? What does a parse tree look like in terms of objects? Okay, so a tree we mentioned must have a root. Okay, now for us, we assume the root is program. Now, if we create something more generic, we can maybe assume the root can be anything. We are building a parse tree specifically for representing a programming language. Whereas in this example over here, this is a parse tree for representing sentences, the parts of a sentence, where a book contains a whole bunch of sentences. So you could have a parse tree for a book that contains a whole bunch of sentences. That would be kind of like our program. Or you could have a parse tree just for a sentence. A tree, if we go back to this, a tree can be described as a tree of trees, something like that. A tree can be described as a tree of trees. So if I go back and I look at my picture here, this whole tree has a single root. Now, what if I'm looking at this part right here? Is that guy a tree? Sure, he's a tree in and of himself. I have a single root here. This is a test. And here are my branches off of that tree. Is this guy here a tree? He is. Pretty simple tree. He's an expression, where this expression is of a certain type. And here's a piece of information. So not a complex tree. It only has one branch, which is just an extension of the trunk. All right, so this guy is an uninteresting tree, but he's still a tree. All right, so this is a collection. A tree is a collection of trees, tree of trees. All right, so when we're talking about implementing a parse tree, it must have a root. We assume the root is program in our case, even though we've seen, we could have the root being sentence or something like that. We're building something specifically for programming languages. All right. But then we're going to say a tree is a collection of trees. So what are the possible root types in our language, in our programming language? If I look at this map here, I see one root type as a program. I see another root type is a statement. I see another root type is an expression. So we have program, statement, expression. Those are the different kinds of root types that could be the top level, well, that could be contained within our program. Now, if we're designing a language, would a language ever allow us to have programs inside of it? Or is the top level trunk always program? And then that would be the last time we'd ever see the internal. I'm asking, in a picture like this, would we always see program at top? And would we never see program anywhere else in here? Is that a true statement?
Yeah, we do see like in terms of a file.
Well, we're still talking about it being generic. So the idea here being that as a language designer, we get to choose what is the most abstract way, the abstract way of talking about our computer program. Is there something more abstract? Can we have or maybe this is what you were getting at, where you have a file system that has a collection of programs in it.
Yeah.
Okay, yeah. So maybe, and we could say, yes, that's true, but now we're solving a different problem. Now we're solving the problem of creating a file system, no longer solving the problem of creating a programming language, right? So in the world of creating a programming language, the top level thing will always be a program. That's my source. We have the source code for a program that we then need to turn into something else. So at the top level here, we have a root that always is programmed. So we have a single package. If we have 10 different programs that we've written, each one of those programs would have a parse tree associated with it. Now, the parse tree associated with that program could be part of a more complex tree, although typically when, if you're talking about file systems here, you would have a hierarchical tree-based directory structure, like POSIX-based, like Linux, where it has a root directory at the very top, and then within that you have other named directories, and in that you have other named directories, and you have your leaf nodes are actually files, but then it doesn't go farther than that. Files are things you might further parse, like in our case, if the file is of type, Java program, then it would go through some sort of program that created a parse tree out of Java syntax, something like that, where the top level would be program. So in that particular example, you wouldn't have the same data structure representing a file system as well as a parse tree for a programming language. They would be similar data structures in that they're both trees, but they, if a data structure would only go so far as to say, I store files. And once you get to a leaf node of this tree, which is a file, then I might do different things with those files depending on the MIME type of that file, for example. Okay, so we're going to say for us at the highest level, all of our trees start with a program. And that's the only place that we see program in there. The rest of our tree is made up of a collection of statements and expressions. All right, I think that's true in this tree right here. Program at the top. A program is a collection of statements. I've only represented a single statement here. But if I look at Eclipse, this particular program has 1, 2, 3, 4, 5, 6, 7 statements in it. So when I run this program, I run it sequentially. So from left to right, let's say, in our tree structure. So this would be the far left statement, statement next to that, the statement next to that, the statement next to that, statement next to that, so on and so forth. So I would execute it. I would prepare it for my interpreter from left to right, because that's the order in which I found those statements. But as I'm walking through this program, I create a new branch for each statement. And then within each of those statements, I might create branches for the kind of statement it is, and that we saw that with like our while loop. So this is a statement that had a whole lot of complexity afterwards when we got into this. So these, our while statement here, the left tree was fairly simple. The right tree got pretty crazy, and extra crazy, really, the farther right we went here within this statement. All right, so we are dictating an order of how we choose to use this tree. But in terms of the nature of the tree, we have a top level program, and then we have a collection of statements. And statements are collections of statements as well as expressions that we've invented as the syntax of our language. All right, so implementing a parse tree, we're going to have a root that's always programmed, and then it's going to have trees within that. So we're calling it a tree within a tree, but we're dictating a beginning. We're saying the beginning is always programmed. And then within that, we have this collection that is any one of our subtype trees, which is either a tree that starts with a statement or a tree that starts with an expression. A statement tree or an expression tree, something like that. So if we're thinking about this in terms of objects, we have something called the program tree object, okay? And a program tree will have in it a collection of statement trees. These are the statement branches that immediately come off the main trunk. Main trunk. Okay, main trunk. So a program tree will be a collection of statement trees. If I look at my picture here, that's all a program is. Collection of statement trees. All right, so this guy's actually pretty simple here at the top level. So let's get into what a statement tree is. We might add some stuff to that. All right, statement tree. Okay, we'll call a statement tree object. Okay, a statement tree object. If I go and look at my picture here, okay, what's a statement tree? It's a collection of, well, it's going to be a type of statement, specific kind of statement that's going to be a statement tree. So it's going to be a type, and then it's going to have a collection of expressions and or statements, because some statements, like a while statement, is a more complex statement where it has a expression, where expressions are things that can't stand on their own, and statements, things that could stand on their own but could be embedded within other statements. All right, so we're going to have inside of our possible statement tree, we're going to have branches that are representative of our different kinds of statements. Okay, so a statement tree will be the kind of statement. Kind of statement, and then a collection of, I call these guys part trees. Part trees being trees that are parts of statements. Okay, now hopefully you'll see a pattern emerge here in a second. So now I'm going to create a part tree object. Okay, a part tree object is a type. Go back to my picture here. Okay, so here's my program. A program is a collection of statements, but really we can say a program is, well, let's say what it is. A program is a collection of statements, where a statement is a collection of parts, where those parts can be expressions or other statements. So really a program is a collection of part statements, where those part statements would always be, the top level would always be statements. That just happens to be a rule that we don't necessarily need to enforce. It would be something that we pre-enforce by the design of the language. We would say that expressions are only found inside of statements. We never find expressions sitting there on their own. That's how the language that we're writing works. Okay, so we'll have a program is made up of a collection of part trees, where a part tree can either be a statement tree or a expression tree. So my question here is, are statement trees and expression trees different from each other? If I'm looking at this picture, is there a difference between a statement tree and an expression tree? This is an expression tree. This is an expression tree. Here actually is, we would probably still have to call this guy a tree. So this guy would be a symbol tree, probably, if we were going to call it something generic, because in this case it's a Boolean operator, but you have other kinds of symbols that will exist inside of our operators that exist inside of our language. Equal signs, plus signs, minus signs, divide, things like that. Those guys are part of our tree structure. Okay, hence the reason I'm calling them part trees. All right, so
I have a question.
sure.
Do you want to make the expression tree valid as a statement?
I would say probably not, but that's going to be more of the rules of our language, not something we necessarily need to enforce at the programming level. But the
So
programming, oh, go ahead.
that is my question. I think program are collections of statement. That's definitely no problem. Then technically statements should still be statement tree rather than expression tree. But statement tree can be made from expression tree and other keywords.
And other statements.
Yeah.
Yeah. So if you want to keep it very defined, you don't want to have. So really, I'm kind of defining maybe a hierarchy type thing here. Let's go your route. So you're saying a program tree is a collection of statement trees, where a statement tree is a kind of statement, and it's a collection of expression trees or statement trees.
Or combination.
Well, it would naturally become a combination. Oh, I get what you're saying. I'm saying collection of these guys. So we're saying the same thing. Collection of a combination of those guys. So it's any kind of guy like this. Now, in object-oriented programming, how do we say that, okay, I have expression trees and I have statement trees. I need these guys all to be of a certain kind so I can have a collection of that kind. Well, that means you need to have a parent of these two that is the generic form of them, which is I was calling a part tree. A part tree is a type, either statement or expression, or as we just kind of saw here, could be an op tree. But those make up the parts of our language. So I would put it like this: a program tree is a collection of statement trees where that top level must be a statement tree. It has to be that kind. But a statement tree is a kind of statement, and then it has a collection of part trees, which handles this idea, that combination of expression or statement or operator.
Sure.
Where a part tree has we can call it a part type. So we can even describe it in here. Part type might be statement, expression, operator. I'll put ... in case we add other types to that, but those are the kinds of parts that make up our language, right? So that's what a part tree is. Now up here, we're going to say that a statement tree object extends part tree. So statement trees have a kind of statement and a collection of part trees underneath them. But a statement tree in and of itself is a part tree. Where a part tree extends generic object for right now. We could decide there might be something higher than that, but this guy is basically a top level object. A part tree is a top level object which keeps track of what kind of part it is.
Should it just extend from tree object?
Only if, I mean, we might change it to that, but right now we don't have something called a tree object.
I
Where's
just say you might can create a generic tree first.
Potentially, but I'm not sure it's going to get any more generic than a part tree. Because a part tree here is just a part type as far as we have it right now. We're not going to add anything else to this for right now. So we're saying a part tree is simple. I'm not sure we're going to get any simpler. We're not going to be able to break it down any more than this for right now, based on the way we're kind of thinking about this. Okay, so a part tree right now is just a general plain Jane object that has a part type. Now, we already have seen that we have two different kinds of part trees. So if I'm going to draw a picture of my objects here, I have generic object, okay, which we didn't write, so I'll put that in red. I'll have a part tree, which is an abstract class, because we won't actually have plain Jane part trees sitting out there. Instead, we have things that are part trees. And what things are part trees? Well, we have statement tree. We have expression tree. I'll go ahead and throw my op tree in here because we already find those guys in the wild. We might actually end up calling them something called a symbol tree. I'll show you back in here, like this is a symbol. This is a symbol. This is a symbol. So these guys are actually examples of our leaf nodes in our tree, which are trees with no children. So we'll call this guy a symbol tree for right now. So those are the things that make up our where a statement tree is a collection of, well, it's a type and then a collection of part trees. So we won't represent that here. This is the object-oriented model for this. And then I'll steal this. Now we have something that we're inventing called a program tree. Program tree comes from a generic object and represents a collection of part trees. Where a part tree is a statement tree, an expression tree, or a symbol tree. Collections of those. But these guys are, a statement tree is a part tree. Expression tree is a part tree. A symbol tree is a part tree. A program tree is just a basic object. All right. And all part trees, we've said, have a part type. All part trees have a part type. All statement trees, we've kind of described it here, will have a, well, I'm going to say it's a kind of statement here. How you represent it, you can decide, as well as a collection of part trees. An expression tree is just the symbol. I'm sorry. Symbol tree is just a symbol. An expression tree when we talk about expressions, expressions are collection of expression trees. Spread these out a little bit. Go back and look at our picture here. Whenever I run into something that is an expression, expression is a collection of expression trees. A statement is a collection of expressions or statements. So these are parts. Here's a statement. It's a collection of part trees. Here's a statement. It's a collection of part trees. Here's another statement. Here's a collection of part trees. Here's an expression. It's a collection. So an expression in this case has a single symbol associated with it. Okay, so an expression is a collection of go back here. An expression is a collection of expression trees and symbol trees. So we can say it's a collection of part trees, but we'll never find a part that is a statement tree inside of it. So the way we say it's a collection of these two kinds of guys is by saying, oh, it's actually a collection of part trees. Now, I could break it down another level and say that we have this idea of a part tree. And then from there, we have an expression part. And we have a statement part. Where a statement tree is a statement part. So actually, let's move these guys over. Okay, so a part tree comes in two flavors, a statement part or an expression part. A statement part is a statement tree, which has inside of it a collection of anything that's a part tree. An expression part can either be an expression tree or a symbol tree, or an expression tree has a collection of expression parts. And a symbol tree has just a symbol. So I think this would be a reasonable way of representing our objects here, our base level objects. So if I come down here and I do something like this, Java created. This is my color-coded key here. Java created that. We created abstract class. And then this is a we created class. So anything in red here is part of the Java language. You don't have to write that. Anything in yellow, we're writing as an abstract class, meaning that we don't intend to create instances of it. Anything in green is written as a class that inherits from that abstract class, because it is a something we do intend. We will actually see statement trees in the wild and expression trees in the wild. We won't see statement parts. We'll see things that are statement parts. We'll see things that are expression parts, but we'll never actually just see a generic expression part. We see either expression trees or symbol trees. All right, where a program is a collection of statement trees. Collection of statement trees. So homework, starting a new project. Actually, we probably don't want to start a brand new project for it. We'll build it inside of our code. So add the new objects that follow the inheritance model depicted in the previous slide. Make sure to make abstract classes abstract. Make sure to properly use the parent constructors. I'm going to say when it makes sense. All right, so that'll be it for homework for Wednesday. So we're not actually doing anything with these things yet. You're just building the components. So you're going to create, so if you're just listening to me out loud here, I'm going to basically tell you what you need to do for the homework. You're going to create a class called part3. It'll be its own Java file. You'll create a class called statement part, a class called expression part. All three of these guys will be defined as abstract classes. You'll build a class called statement tree, a class called expression tree, a class called symbol tree. All these guys will either inherit from, well, statement tree will inherit from statement part, expression tree will inherit from expression part, symbol tree will inherit from expression part, expression part will inherit from part tree, statement part will inherit from part tree. Okay, and then your statement tree will have a collection of part trees in it. So this will probably be an array list of part trees. An expression tree will be a collection of expression parts. It'll probably be an array list of expression parts. And a symbol tree will be a single symbol, probably a string. Your program tree, we will actually create an instance of programming trees. So this guy would be not an abstract class. And he's going to have a collection of statement trees. So probably an array list of these guys. So the homework is to just build these objects. All right, we're not putting them together yet. We're not creating instances of these guys. Ultimately, we're going to use these objects to build something like this. But for the homework for Wednesday, all we're doing is creating these objects. We'll go ahead and add this. So homework 12. I'm going to say in the slide set here. Make sure to make abstract classes abstract. Make sure to use properly. Make sure to properly use the parent constructors when it makes sense. Submit a GitHub link to the entire project. I will only be looking at the new objects created. Submit the self-evaluation. Okay, and this is due on Wednesday at 10 a.m. All right. So that's it for today. Questions about what I'm asking you to do? Shouldn't be. Go ahead. What was the question?
So besides creating the abstract, so I was asking about the body of the classes. So besides creating the abstract class, for the body, we have to create like constructors or methods.
Well, you'll create methods when it makes sense to make methods. You're just creating these. For your homework, you should create 1, 2, 3. Well, here, for your homework, you should create 3 abstract classes and 4 normal classes. So you should have a total of 7 new files that you're going to create for your homework. And those guys should have in them what they need to have in them to create this inheritance model. So this guy inherits from this guy inherits from this guy. All 3 of these, though, are abstract classes because we're not going to create instances ourselves. So this guy inherits from him, this guy inherits from him, this guy inherits from him. This guy doesn't inherit from anybody. He's your top level program tree. Well, he technically inherits from object, which isn't in our control. So you're going to create 7 new classes for your homework with the appropriate constructors and methods you might need. But you're not going to use them yet. You're just creating these Legos, these building blocks. All right. All right. I will see everybody on Wednesday. And the slides are updated on Blackboard. They update automatically. Have a good one.